Hi everyone, I'm James Holland, and today I'll be presenting our work on a new website fingerprinting defense called Regulator. This work was done alongside my advisor, Professor Nicholas Hopper, and at the University of Minnesota. To provide a short summary, Tor is a popular low-latency anonymity network that protects the privacy of its users' internet browsing habits. It does this by encrypting traffic while routing it through a circuit of 3 volunteer-run nodes, preventing any single node from knowing both the origin and the destination of the traffic. The encryption strategy, known as onion routing, is characterized by a message encapsulated by multiple layers of encryption. Each successive Tor relay strips a layer of encryption from the traffic and routes it to the revealed address. Then, for example, if an attacker is capturing traffic between the user and the guard node, the attacker will be unable to determine the destination of the traffic. In the last decade, Tor's user base has increased to millions of daily users. Over the same period, a series of papers have shown that Tor is vulnerable to a type of traffic analysis called website fingerprinting. This attack is characterized by a passive local adversary who eavesdrops on encrypted traffic to determine which web pages a client is visiting. This adversary can be anyone with access to traffic between the client and guard, including the guard itself. The attacker typically uses patterns in traffic metadata, including packet timing, the sequence of upload and download packets, and the traffic volume. More specifically, an attacker can run web crawls to create a database of associated website traffic pairs. Early approaches used custom features and machine learning techniques like k-nearest neighbors and support vector machines to create predictive models. These models typically input captured traffic metadata and output a website prediction. Where early attacks struggled to reach the required degree of effectiveness for real-world use, more recent techniques have leveraged large datasets and convolutional neural networks to significantly increase attack accuracy, making the website fingerprinting attack more threatening. In response, a variety of website fingerprinting defenses have been developed. Defenses typically operate by delaying traffic and by inserting dummy traffic. However, previous defenses have generally been defeated by existing attacks, incur high bandwidth and latency costs, or require additional infrastructure. Regularizing defenses, like Tamara or Dynaflow, tend to be the most effective as they make the traffic associated with many different web pages look alike, thus preventing accurate classification. They operate by buffering traffic and sending it at a preset rate. If no real traffic is available, then dummy traffic is sent instead. However, real traffic often doesn't match the set rate. As a result, excessive bandwidth and latency overhead is often occurred. However, one can regularize traffic without relying on constant rate approaches. To demonstrate, I'll first present characteristics of real-world traffic that allow for effective but efficient defense. First of all, real traffic is particularly bursty in the sense that much of the volume is sent in quick bursts with long and irregular gaps between the bursts. Several different example traces are given in the figure on the left. As you can see, much of the web page is downloaded quickly, though sometimes the page load may have a long tail. In fact, in the deep fingerprinting dataset presented by Surinam et al., we find that the interquartile range, on average, of the traffic timing is about 4 seconds, compared to a 28-second average loading time. Additionally, surge patterns are fairly predictable in the sense that most of the traffic is sent soon after the web page download begins, as shown in the middle figure. In the same dataset, the median packet is sent just 7.5 seconds after the 10th packet. Lastly, the upload packet timing imitates the download packet timing. As shown in the right figure, the upload sending rate is heavily correlated with the download sending rate, though at lower volumes. This isn't particularly surprising given how web browsers request data, which is then sent by the server in response, but it is a useful property for the regulator defense. So the intuition behind the regulator design is to regularize the download packet surges so that the sequence of packets and the packet timing information in the download leaks less information about the destination website, while at the same time sending upload traffic as a function of the download traffic. This way the upload traffic leaks more information about the website as well. And to set up the defense, the client pads the upload packets, and then the Tor bridge or middle node pads the download packets. And the download traffic is sent at initial surge rate R and decay rate D, so that RD to the T packets are sent at time T. So in this case, if the decay rate is 0.9, for example, then the number of packets sent at second 7 is 0.9, the number of packets sent at second 6. And then T is the number of seconds since the last surge. So this is basically to make it so that at the beginning of a surge, a large number of packets are sent, but this sort of rate decays a few seconds after the surge. And then if the number of delayed packets grows to a set multiple, or capital T, of the target rate, then a new surge is sent. So this basically means that the number of packets already waiting in the buffer has gotten large, and so the defense should send a new surge of packets to make it so that the latency doesn't grow too high. And then the padding budget is drawn from a uniform distribution, 0 to n. This is partially to cap the amount of bandwidth that can be added, and it's also to make it so that the amount of padding packets is somewhat random, so that the packet sequences associated with a given web page or really website are randomized somewhat, making it harder for a classifier to classify them. And the upload packets are sent as a fraction of the download packet rate. This is to make it so that the real upload packets never have to wait very long to be sent, while also making it so that the upload packets don't leak any further information because they're sent at this constant rate. And the upload packets are also never delayed more than a certain cap, or C, seconds. This is to make it so that the added latency doesn't grow too high. Of course, there's still the difficulty finding the optimal parameters to use in this defense. This is similar to the problem of hyperparameter optimization that's often found in machine learning. And while we could use something like random search or grid search, we chose one of the Bayesian methods, tree-structured Parson estimators, which sort of explores possible combinations to find out which ones are high-performing, and then sort of further varies those to find better combinations. And we ended up picking two of these higher performing combinations that demonstrate different trade-offs between the overhead and the performance. Regulator Heavy and Regulator Light, where Regulator Heavy uses more bandwidth and a slightly better latency, but also has better defense effectiveness, and Regulator Light, which is somewhat less effective but uses less additional bandwidth. And then here's an illustration of the regulator defense. So you can see in the undefended traffic, there are a couple sort of large surges of download traffic that occurred around 3 and 7 seconds in, though in this case upload traffic is fairly constant. And then the defended traffic sends a fair amount of traffic early, but then when these surges come in, it delays some of those packets to form this sort of curved pattern. In that way, if you use the same pattern in a lot of the different websites, then it becomes difficult to classify this traffic with its associated web page. But at the same time, it doesn't delay traffic very much or add too much additional packets. And then to evaluate regulator, we simulate it on a few data sets, primarily the data set provided by Surinam et al. For their deep fingerprinting work. And then we compare regulator to other defenses in both the closed world and the open world settings. And to provide a quick recap, the closed world setting is one where the attacker simply has to determine which of a number of set number of websites, in this case 95, the packet sequence or trace is associated with. So this is basically just a straightforward classification problem. And the other one's more realistic but somewhat harder, where there's a set of monitored or censored websites, as well as a set of websites that the attacker cannot train on in the open world, and the attacker has to determine whether a certain new packet sequence is associated with a website that's in this censored or monitored set, or it belongs to a website that the attacker has not seen before. And this is a fairly difficult setting, but it's much more realistic. And then the data set we use here has 1,000 instances of each of the 95 monitored sites, but about 41,000 web visits in the associated with non-monitored websites. And then each defense is just simulated on the data set to produce a defended data set, and we test the defense effectiveness by seeing how far or how much it can lower the website fingerprinting attack effectiveness on this data set. So here are some of the overhead and the closed world results. As you can see, the Tamara overhead is very high, at around 30% latency and maybe 200% bandwidth addition. Though of course it does very well in terms of defense effectiveness, and it's mostly just used here as a sort of benchmark to see how good a website fingerprinting defense could get. WTF-PAT has a moderate bandwidth, but it's only really effective against QML. It's not effective against the deep learning attacks. Front, it has more moderate bandwidth, though it's somewhat higher than WTF-PAT. It has some effectiveness against TikTok and deep fingerprinting, the two deep learning attacks. And then Regulator Light has it has some latency at 8.9%, but fairly moderate bandwidth. It does very well against TikTok and deep fingerprinting, getting TikTok down to about 35% and deep fingerprinting down to 23%. And then Regulator Heavy further sort of extends this lead, though it has somewhat higher bandwidth. It gets TikTok down to a 25% accuracy and deep fingerprinting down to about 20% accuracy. So for the open world results, we see something similar where, and I guess to provide a bit of background, we use precision and recall here, because using accuracy isn't particularly useful due to the base rate fallacy, where you can have an attack that appears to do well in the open world because it might have a fairly high accuracy percent, but if the number of its false positives starts to actually drown out the number of the true positives, which can happen when the monitored set is much smaller than the unmonitored set, then the attack with high accuracy might not actually be very useful. So here we use the precision in recall to compare the defenses. And as you can see, against both TikTok and deep fingerprinting, Regulator drives down the precision in recall curve a fair amount, making it so that the attacker really has to choose between high precision and high recall, and has a difficulty identifying many of the packet sequences very well without really high false positive rate. So in conclusion, Regulator provides an effective defense with similar or lessened overhead compared to other moderate overhead defenses. Regulator can be implemented in a fairly straightforward manner. It doesn't require any additional infrastructure. Future work could include applying it to the setting where the user may visit multiple different web pages of the same website, potentially making the packet sequence easier to identify if the data set includes multiple web pages of a certain domain. And one could also look into how Regulator could also provide effective defense against the flow correlation attack, which is a different class of traffic analysis attack against Tor.